In this video, we're going to interactively develop the simulation and visualization that I presented to you as an executing script in the preceding video. Now, IPython has built-in Matplotlib support for the Matplotlib visualization library, and thus also has built-in support for Seaborn because Seaborn simply executes on top of Matplotlib, and those two libraries will use a couple of different features from both of them to implement the visualization that you saw in the preceding video. Now, in order to enable interactive visualization creation in the context of IPython, you have to supply the --matplotlib command line argument. There's also a way to enable it in an existing IPython session as well with a so-called magic, and I'll talk about that again in just a moment here. So if I go and execute IPython command with the --matplotlib, we get our normal introduction to the fact that we're running the interactive interpreter, but it also adds in an extra line, which, by the way, will differ based on the operating system that you're using by default. But this is telling us what graphics package is being used underneath the hood to actually support the visualization that we're implementing. And there's various different Matplotlib backends available. Those are sometimes operating system specific. I typically just work with the default one for most of what I'm doing. However, sometimes there are features that are only supported by specific backends. I don't believe we have any specific features like that in the examples that I'll be presenting to you. Now, once we've entered IPython, if by any chance we had forgotten to enable Matplotlib, or if we're in the middle of an extensive session and we don't want to restart, we can also use what's known as a magic. We can say %matplotlib, and then if we were to press enter, that would enable Matplotlib mode in the IPython interactive environment. If you're working in the context of a notebook, a Jupyter notebook, the command would be matplotlib inline with the % in front of it. And in fact, if you load up the corresponding notebook for this video, you will indeed see this inside the first cell of that notebook. All right, let me go ahead and get rid of that, and let's start talking about the code now that's going to enable us to develop this interactively. Now, the first thing I'm going to do is bring in each of 4 different libraries that we're going to be using and talk a little bit about each one. So again, we're taking advantage of this Matplotlib library to do visualization, and in particular we're going to use a sub package within that library called pyplot, which is going to give us the capability of getting a window up on the screen, and Seaborn will then use that window to display the graph that we're going to create. Now, when you import Matplotlib's pyplot sub package, then most people import that as PLT. That's the recommendation from the Matplotlib documentation. So that's what we're going to do here, and then we can access the features of this module via PLT and a dot. So we'll see that in a couple of situations shortly. So that's one of the libraries. Next, we're going to import a library that we're actually going to talk about in a lot more detail in a subsequent lesson, the Numpy library, which by convention is imported as NP as its shorthand. And specifically, we're going to be taking advantage of that library's unique function to determine the unique die faces that are rolled. And to summarize those roles as well. So you're going to see a pretty interesting function in terms of the power of that function that's provided to you in a few moments here. We're also going to import the random module, and that will be so that we can do our random number generation to produce the die rolls. And finally, we're also going to import the Seaborn library, and this particular library by convention is imported as SNS, which is actually a joke from the creator of the Seaborn module. So if you're interested in finding out the background of why SNS is used, I would suggest that you look that one up online. It is actually a little bit of an interesting background story. So those are the 4 libraries that we're going to be taking advantage of, and the next thing that we need to do is to roll the dice so that we can calculate the frequencies of each of the faces and use those as part of our plotting of the information. So for that purpose, I'm going to go ahead and copy and paste a snippet here, which is a list comprehension that is going to iterate 600 times. So for I in the range 600 is going to go 0 through 599, and for each of those values we're simply going to use our random module's randrange function to produce values from 1 up to but not including 7. So give me a random number from 1 to 6 for each iteration of this list comprehension, and the resulting list is then going to have that many items in it. And of course, if we were doing 60,000 roles, then we would put 60,000 here. If we were doing 6 million roles, then we would put 6 million here. So now that we have the die rolls, we need to summarize them and count the frequencies of each. Now, of course, because we have a list, we could kind of do that manually on our own, but one of the great things about Python and libraries is that much of what we need to do has already been implemented, so we can think at a bit of a higher level in Python. So this one statement that I just pasted in is going to take advantage of the Numpy library's unique function to summarize the sequence that's provided as the first argument here. Now, Numpy is typically used to work with NumPy arrays, but Python is super flexible in many ways. So often where an array is required by NumPy, you can also work with a list or any other sequence of values, and vice versa as well. So anywhere a list might be used in a regular Python script, you can often provide a NumPy array. So you get a lot of interchangeability between types in Python because of the way the language works with its dynamic typing. So the NumPy unique function is going to look at the sequence you give it as the first argument and find all the unique values within that sequence. And if you happen to provide the second argument, return counts equals true, the default for that, by the way, is false, it's going to also count how many occurrences of each of those unique values there are in that first argument sequence. Now, if you only give NumPy unique a sequence as an argument, it will simply return a collection that contains just the unique values. But if you give it both of these arguments, it's going to give you back a tuple containing 2 sequences, one that contains the unique values and one that contains the frequencies of those values. Now, the actual type of those sequences that's returned is, each of them is a NumPy array data structure. And even though we're not talking about NumPy arrays in this lesson, because NumPy arrays can be treated as sequences, we can use them as if they're lists or tuples in our Python code. So without you even knowing anything about NumPy arrays yet, you're able to take advantage of this nice function that performs a key task that we need for this example. And we'll talk in detail about NumPy arrays 2 lessons from now, and at that point we'll revisit the unique function as well. So after this one statement, we're able to perform this powerful task of summarizing a sequence no matter how long it is and finding out what its unique values are and what the frequencies of those values are. So let me go ahead and execute that. And at this point, we're now ready to begin the plotting of that data. So this is the data that we're interested in. We have the unique set of values and the frequencies of those values, and now we want to create what Seaborn refers to as a bar plot containing a visualization of that data. Now, for that purpose, I'm going to start out by creating a string, which is going to become the title of the bar plot that we're creating. This formatted string, notice the F at the beginning of it, is going to contain a bunch of literal characters and one placeholder where we will insert how many die rolls there were. So that's the length of the rolls list, and we are using a little bit of formatting here. We've got a format specifier containing just a comma, and that is the thousands separator. So for example, if we did 60,000 as the number of dice instead of 600, then when we get this formatted string, it would contain 60, 000 for the formatting of that numeric value. Next, we're going to start configuring the options for the plot that we're about to display. So for this purpose, we're going to be using the Seaborn setStyle function, and we're going to give it the argument white grid. Now, a couple of things here. First of all, when we're working with Seaborn, because we imported it as SNS, we're going to use SNS dot to access the capabilities of that module. Second, the setStyle function, obviously you need to learn about the different functions that are part of Seaborn, and they provide extensive documentation on that. But you may be wondering, for this function, what is white grid? So in Seaborn, when you create a graph by default, you get a white background with nothing in it. When you select white grid, you also get a white background, but it provides lines that help you understand the magnitudes of the values being plotted. So as you're about to see in the next snippet, when we actually create the bar plot, we're going to get vertical bars by default, and the white grid is going to display horizontal gray lines that we can use visually to help us understand the magnitudes of the bars that are being plotted. Now, I'll go ahead and execute that, but let's also jump over to the Seaborn documentation for a moment here, which you can find at this website. And you'll notice there's a nice search field up here in the upper right corner, and let's say we want to learn more about setStyle, and of course anytime you use any new feature you should dig into it and learn about all the different possibilities. So let's execute that search, and you can see when they display their results they don't use SNS as the name of the module, they use the actual module name. But let me pull up setStyle here, and I'm going to just increase this font size a little bit, but you can see setStyle actually takes two arguments, even though we only provided one. The first argument is the style argument, so if you don't provide keyword names for each argument that you supply, then it's going to assume the first item represents the style and the second item represents whatever RC is. Now, we're only using the style argument. RC and style both have default values of none in Python, which is Python's constant representing nothing. And for the style, we happen to have chosen white grid. And by the way, down below here, they show you a sample of how to use, or a couple of samples of how to use the setStyle function. Now, there's actually several different possible arguments here. We chose white grid because we wanted to get those horizontal gray lines that will help somebody reading our bar plot understand the magnitudes of those bars a little bit better. So that's why we chose that particular value. Now, as you get into Seaborn or any other library that you may take advantage of, you are going to want to take the time to look at the online documentation for each of the new features that you're looking at. It will also help you become more familiar with Python programming in general. Now let's switch back over to the source code here, and now that we've specified the background for the plot, let's actually create the plot. And this is going to be one of those examples of the power of Python and libraries. In Python, as I've said before, lots of the things you want to be able to do in many common applications have already been implemented for you. In the case of Seaborn, it has a bar plot function that already knows how to create a bar plot. And these are the arguments that we've chosen, but as I'm going to show you in the online documentation momentarily, there are actually lots of different possible parameters for the bar plot function, and therefore lots of different ways you can call this function. So before I get into all the details here, let me just go and execute this. And one of the reasons, by the way, that I have my IPython interactive session offset here from the full screen was so that I could have this diagram pop up, and so I'll be able to click back and forth between the windows. So you can see here, simply by executing that one statement, we were able to produce a very nice looking bar plot, and it did all the work for us. We supplied some data. It figured out how to get everything on the screen. It figured out how to set the values on each of the axes. It figured out how to plot the bars and what the lengths of those bars should be. And by the way, the white grid, you can see the box around the bar plot, and you see these gray horizontal lines which help you read the bar plot. So we can see anything that goes above 100 had a frequency that was higher than 100. Anything below that line obviously had a frequency that was less than 100. And in this example, remember, we rolled the die 600 times, so really we expect each of these 6 bars to be right around 100. And as we get into higher numbers of die rolls, we'll see these bars once again even out a little bit. Now, you will notice that the die face values are along the x-axis at the bottom here. The frequency values are along the y-axis, but we don't have the title of the bar plot yet. We don't have the text that we had put at the left and bottom edges of the bar plot yet. These are pieces that we're going to get to in the source code momentarily. So let's go back and look at this bar plot call, and also I want to take a look briefly at the documentation for bar plot as well. So it turns out bar plot actually has, I think, a couple dozen different parameters that are available to you, all of which have default values, which enables you to call bar plot numerous different ways. In this case, we chose to provide only 3 parameters to get the bar plot that you see over here. So the first parameter we supplied using the keyword argument syntax is the set of values that should be plotted along the x-axis. Well, that is the set of unique faces for the roles list that we supplied to the numpy unique function. And by the way, I should mention that it automatically orders those values in increasing order as well. So you'll notice that we got 1 through 6 as those unique values. The second argument we supplied here is the values to be plotted along the y-axis, the frequency of each die face. So frequencies again was calculated up here by numpy unique. And then the last argument we supplied was one of the many different palettes that are available to you. You can create custom palettes with precise colors that you want to use. You can set a fixed color for all the bars, so if you don't want to have different color bars for each bar, you don't need to. And in fact, the colors are not meaningful in this graph. We use them just to make it look nice, but in reality, when you use different colors in most graphs, that can have meaning associated with it as well. So it might actually be better practice for a simple bar plot like this, since there's no meaning to the colors, to just use one color for all of the bars. But we did indeed choose the palette called bright. So let's talk about 2 things in the docs next. Let's talk about the bar plot function first, and then I'll talk about the palettes as well. So let me go back to the Seaborn documentation here, and let's search for bar plot. And the main reason I want to do this is to show you that there's a massive number of parameters available to you for the bar plot function. And all of these parameters are discussed in this web page down below. And then they generally are going to, after the discussion, provide examples that show you different types of bar plots, in this case, that you can draw, and what the arguments were that produced those bar plots as well. Now, the reason I wanted to show you this particular bar plot documentation is because of the large parameter list. I mentioned this in an earlier lesson, that in Python, rather than having a bunch of different functions that have the same name and different parameter lists, it's often the case that you'll have one function with a massive number of parameters, all of which have default argument values for those parameters. And that means that you're that it's very easy to take advantage of what Seaborn considers the default values for every single parameter, and you can just supply the couple of parameters you need in order to accomplish the task at hand. So again, we supplied the x and y values as well as the palette value to get the graph that was produced over here. Now, separately, we also, like I said, worked with the color palettes. So for this one, I'll just type in the URL rather than searching. But in the Seaborn tutorial, if I can type here, in Seaborn tutorial, there is a color palettes page. So let me bring that up. And they talk about the various ways in which you can choose color palettes here. You can create custom palettes or take advantage of built-in ones. And I just want to scroll through this page to show you that there are different color palettes that are predefined. So this is one color palette that actually has various different versions. We're using the bright color palette at the moment, but you can see they provide a bunch of other options for that same palette as well. And then there's other color palettes that are predefined, and there's ways to create custom color palettes as well. So you've got lots of different capabilities. In addition, Matplotlib itself provides a ton of different color palettes, and you can take advantage of both of those sets of color palettes, the ones from Seaborn and the ones from Matplotlib, when you are working in Seaborn. All right, so at this point we have created the initial bar plot. We have we have not only rolled the dice but also created the initial bar plot, and now what we want to do is start finishing off the diagram. And again, this is interactively developing the diagram, so as we execute code that modifies this now in interactive IPython, we're going to see the changes appear over here. So the next thing that we're going to do is add our title to the window. Now I should have mentioned, by the way, the return value from barplot is to give back what's known as an axes object in Matplotlib. The axes object represents the graph and contains the bar objects that are being plotted here, and it also contains all of the other information that is being plotted on the screen. Now the reason that's important is we can then use that axes object's methods to perform other tasks on that graph. So the axes object has a setTitle method, and that setTitle method takes a string argument, which, once we execute this, is going to display the title centered above the graph by default. And as you might expect, there are various options for setting the title. So you can take a look in the Matplotlib online documentation at the class named Axes with a capital A. And in its documentation, you'll find the setTitle method, and then within the setTitle method's description, you'll find the different options that are available to you. Now you'll notice we got some output as a result of that statement that we just executed. The setTitle method actually returns to you a text object that specifies the options for where and that text was displayed and what that text is. We didn't capture that object and store it in a variable, so interactive IPython simply gave me the text representation of that text object, or the string representation, I should say. And in addition, it also attached that text object to the axes object, and that's why it got displayed on the screen. Now we also had provided labels in the graph that I showed you in the preceding video, so I want to get those labels up on the graph here as well. So let me paste in another axes statement. The axes class has a set method, and the set method has lots of different parameters. two of which are the X label and the Y label. And as you might expect, the X label is going to wind up showing up down at the bottom here, and the Y label is going to show up on the left side here by default. And as you also might expect, there are other options that can allow you to customize where those labels get placed. So let me execute that statement, and notice that this set call returned a list of objects, two text objects representing the locations of the two labels and the contents of those labels. And now we can see frequency and die value appearing on the y-axis and the x-axis respectively. Now, you may not recall this, but in the final diagram that I showed you in the preceding video, we also had at the top of every single bar some text saying the total number of roles of that face value and the percentage of the total roles that value represented. So the next thing that we want to do is make some room for that text. We're going to extend the height, if you will, of this axis, or scale I should say, the height of this axis to accommodate some additional text, and then we're going to create that text on a bar by bar basis. So I'm going to copy and paste in our next statement here, and here we're once again using, whoops, I didn't copy it. Let me try that one more time. There we go. So here we're using the setYlim method of our axes object that was created back up here when we called the Seaborn bar plot function. Again, the axes object is from matplotlib, so it's built on top of matplotlib. SetYlim is saying set the limit of the y-axis, and in this case we're taking advantage of the top keyword argument to figure out what the maximum frequency value was. So we're using our built-in Python max function to figure out the maximum of the frequencies, and based on that bar's height we're going to scale the top of the axis to 10% larger than the current top of the axis. So when I execute that, you can see that we're now displaying an additional label here, 120, and all of the bars got a little bit shorter as it scaled the graph in this case, and that's just so that we'll have a little more text room at the top of our tallest of the bars. Now, for this next snippet that I'm going to execute, I definitely need to copy and paste this one because otherwise you'll be watching me type for a long time. We're now going to walk through all of the bars that are in the bar plot, and on a bar by bar basis we are going to perform the following tasks to place the text above each bar. So you'll notice here that we're using a for loop. The for loop is using zip to create the values that will be placed into the variables called bar and frequency. Bar, of course, is going to represent one of the bars, and frequency is going to represent the magnitude of that bar, and we need those pieces of information to figure out where to plot the text and what text to place above each bar as well. Now, the next thing that we're going to do, let's execute this first so that you can see what the results are. So now we have the magnitude and percentage for every bar displayed right above that bar, and the various statements that we've executed inside of this for loop are what are producing those results. So let's walk our way through this snippet so that we can figure out what's going on. So first of all, we're zipping together axes.patches and frequencies. Axes, again, is the axes object that was created by the bar plot function. Patches is a piece of data, a collection inside the axes object that represents all of the patches of color that you see in the bar plot. And those patches of color are actually the bars. So these are the bars in the bar plot. And frequencies, of course, is our collection of the frequencies that are being used to determine the height along the y-axis. We unpack, into bar and frequency the tuples that zip returns based on these two collections. Now, the first thing that we do inside the body of this loop is to calculate the center x coordinate where the text will appear. So you can see that each of these strings is centered above its bar. So we need to figure out from left to right where the center of that text is going to be. So the first thing we do is we get the x coordinate of the current bar. The x coordinate is going to be the leftmost edge of that bar, and we add to that half of the bar's width. So bar.getWidth is going to give me the full width of this bar, which, by the way, is being calculated by default for me when Seaborn's bar plot function creates the bars. So if I were plotting 100 elements, the bars would not be this wide. They'd be scaled down to fit all 100 elements along the x-axis. So all of that calculation is being done for you behind the scenes. So a given bar's x location of its left edge plus half of its width is going to give me the center of the bar along the x-axis. We're also figuring out the height at which that bar should be displayed by calculating each bar's height by calling its getHeight method. So we get the x and y coordinates where we want to display the text. Then we create a formatted string for that text. That format string displays the frequency, and we once again use a 1000 separator. So once we get to higher die totals, then we'll start to see the 1000 separator appearing. And we have a new line in there, so we're creating a multi-line string. And then we have a calculation that's going to be placed into this second placeholder. We're dividing the frequency by the total number of rolls, and we're displaying that as a percentage with 3 digits to the right of the decimal point, and that's giving you the formatting that you see in the second line of each of the strings in the bar plot. So at this point, we figured out where the text needs to go, we figured out what the text should be, and the last thing that we're doing is creating a text object to display on the axes. So again, we're doing this for every individual bar. So each call to axes.text is going to add text at the specified location. So we have the first two arguments, which are the x and y coordinates where the text should be displayed. We have the text to actually display. We chose in this case to set the font size, but you don't have to. You can go with the default font size, or you can change it to whatever value you want. And we also specified some alignment characteristics. For the horizontal alignment, we said to center the text at the location specified. And for the vertical alignment, we said to align the text at the bottom. So basically what's going to happen is at the coordinates specified, which is going to be approximately the tip of my mouse pointer on the screen at the moment, it's going to display up from that point, the text being displayed above the bar and centered at that location. So at this point, we've finally completed the graph as shown in the preceding video when we executed it as a script. But now let's say you're still in interactive mode here, and what you want to do is try this again for a different number of die rolls. Now, you could certainly recall every snippet by up arrowing through all the snippets and individually execute snippets again, but that's kind of a pain. There is actually a IPython magic, a command that you can use to recall prior snippets and execute them again. So let's say, for example, we would now like to perform all of this code again, but we want to do it for 60,000 die rolls instead of 600 die rolls. Well, first of all, we need to roll the dice again in order to do that. So we can see back up here at snippet 5 is where we rolled the dice, and we could certainly up arrow until we recall snippet 5. We could even use backwards searching capability. So if I type Control R here and I type rolls space equals, you can see that it pulls that snippet up again. But instead of doing it that way, let me go ahead and demonstrate the recall IPython magic. So if I say recall snippet number 5 and press enter, it's going to pull up that snippet, and now I can go and edit that snippet to make it 60,000, and I can then execute that snippet again. So I've now just replaced the list roles with a new list that contains 60,000 die rolls. Now, of course, up above here we also went through a whole bunch of other statements to produce the graph over here at the left. So let's say that we now want to redo that graph. Okay, well, we can do that. Let's first go and clear the existing graph. There is in the Matplotlib library, which, by the way, we imported as PLT back in snippet number 1. There is a CLA method, which stands for clear axes. So this is my axes object with all of the information inside of it. So when I execute that, it clears out the window, and this is the default that you would see if you just pop open a Matplotlib window with no data to be displayed in it yet. So we have a fresh figure now, or an empty figure now, in which we can re-execute the snippets from snippet 6 down through snippet 13 here to reproduce the graph with the new sequence of die rolls. So in order to do that, we can once again use the recall command, and this time we can specify it as a range of snippets that we'd like to recall. And again, so just looking up above, snippet 6 is where we calculate the frequencies and the unique values, and then everything else is where we set up and configure our bar plot and all the text in that bar plot. So snippet number 13 was the last of those snippets. So when I say to recall those, it lumps them all together into one large snippet with many statements in it, which as soon as I execute this, the bar plot is going to update. So I'm going to go ahead and do that. And now we can see once again frequency and die value. This time we have approximately 10,000 of each die face because we rolled the die 60,000 times. So notice all the bars are much closer in height than in the preceding graph that we were displaying, and you can see one's a little above, this one's a little below, this one's a little further below, a little above, and a little bit below 10,000 for each of the faces in this case. And of course we could use the same technique again if we wanted to roll the dice again for a different number of rolls. Now there are many of these IPython magics. I'll introduce many more of them as we proceed through these videos, but one other one which I used in order to create the script that I executed for you in the preceding video is the %save magic. This is particularly handy once you've taken the time to write a bunch of code interactively in the context of IPython. So if I want to save the snippets, going back up top here, if I want to save the snippets from snippet 1 all the way down to where I finalized my graph, which was snippet 13, as you might expect, I can say save 1 through 13, and actually I forgot to put in the name of the file where I'd like to put that, so I'm going to call this, just for argument's sake here, temp.py, so that it doesn't write over any other files that I have in the current folder. But this is now going to recall those 13 snippets similar to what I did up above here, and it will then write them into the specified file. So watch what happens when I press enter here. It echoes back all of the snippets that were written out, and at this point, if I terminate my session and list the current directory's contents, you can see there's my temp.py, and if I then display the contents of temp.py, you can see the list of statements that are in there. And of course you can do whatever you want with those statements, such as open up the .py file and edit it into an appropriate script for whatever your task is that you'd like to perform. Now, there is one thing to keep in mind about the code in this .py file. When you are operating in interactive IPython, the Seaborn and Matplotlib methods and functions that cause graphics to be displayed on the screen automatically also cause the window to appear on the screen that's going to contain those graphics. If in fact you're going to execute the code as a script, and you can see this in my rolldi.py that we demonstrated previously, the matplotlib function called show must be called to actually display the window on the screen. So plt.show with an empty set of parentheses will get the matplotlib window that's been configured with graphics to actually appear. So again, take a look in the rolldi.py file to see what we did once we had all of this code. You'll notice that we put in some comments and we reformatted a little bit, but we also have a plt.show method call, or function call rather, in that script file.